When contemplating the origin of the cosmos, what existed prior to the Big Bang? And if there was no prior, what triggered the Big Bang in the first instance? Until a few centuries ago, the response was straightforward. Some eternal deity initiated everything. Even Isaac Newton believed that God created the universe approximately 6,000 years ago. Later, numerous scientists, including a young Albert Einstein, presumed the universe itself to be eternal and everlasting. Naturally, stars could form and perish within it, planets could collide, and civilizations could rise and fall, but on vast spatial scales and over extended durations, it consistently appeared relatively unchanged from how it looks now. Only in the 1930s did convincing proof of the universe's expansion emerge, and in the 1960s, evidence of its inception in the Big Bang was discovered. Such a revolutionary shift in the scientific perspective has not occurred, perhaps, since the acknowledgement of the heliocentric model. However, two equally challenging questions arose. First, what indeed was before the Big Bang? What was the nature of space before it began to expand, and how long did it remain in this primordial condition? Secondly, everything that has a beginning has an end. Therefore, what will be the conclusion of our universe? The British physicist Brian Cox sought to uncover answers to these inquiries, and now, in a groundbreaking revelation, physicist and professor of particle physics Brian Cox has recently asserted that he strongly suspects the universe existed prior to the Big Bang, overturning the theory of our origins. We once believed that the universe emerged in a state that was extremely hot and very dense at the onset of time, which we referred to as the Big Bang. However, we now have strong reasons to believe that the universe existed before that moment, and in that context, it is feasible to discuss a time before the Big Bang. Join us as we delve deeply into how Brian Cox has just challenged the Big Bang theory. Professor Brian Cox has transformed his scientific domain in the 21st century into something accessible to all, consistently contributing to public discourse and discussion. Never hesitant to confront significant questions, the physicist previously addressed the narrative of the Big Bang. The concept of the Big Bang first emerged in the 1920s and 1930s when we gazed at distant galaxies. We uncovered something unusual. The farther away they were, the quicker they seemed to be receding from us. According to Einstein's general relativity predictions, a static universe would be gravitationally unstable. Everything needed to either be moving apart from one another or collapsing towards each other if the fabric of space adhered to his laws. The observation of this apparent recession informed us that the universe was expanding. Today, if objects are moving farther apart as time progresses, it implies they were closer together in the remote past. An expanding universe not only indicates that objects move farther apart over time, it also signifies that the light existing within the universe stretches in wavelength as we advance through time. Since wavelength determines energy, this means the universe cools as we age, and thus, things were hotter in the past. If we extrapolate this far enough back, we arrive at a moment when everything was so hot that even neutral atoms could not form. If this portrayal were accurate, we should observe a residual glow of radiation today in every direction that has cooled to just a few degrees above absolute zero. The discovery of this cosmic microwave background in 1964 by Arno Penzias and Bob Wilson provided a stunning confirmation of the Big Bang. It is therefore tempting to continue extrapolating backwards in time to when the universe was even hotter, denser, and more compact. If you keep moving back, you will encounter a time when it was too hot for atomic nuclei to form, where the radiation was so intense that any bound protons and neutrons would be disintegrated. A time when matter and antimatter pairs could spontaneously arise, as the universe is so energetic that pairs of particles and antiparticles can be created spontaneously. A time when individual protons and neutrons disintegrate into a quark-gluon plasma. This sets up a very different portrayal of the beginning of what led to the Big Bang. Rather than the emergence of time and space from a singular state, now we must address the truly significant questions. What does all of this imply for the genuine beginning of the universe, if such a concept even existed? Well, the fundamental conclusion might be this. The hot Big Bang unquestionably took place, but it does not extend all the way back to an arbitrarily hot and dense condition. Instead, the very early universe underwent a period during which all the energy that would later form the matter and radiation present today was instead contained within the fabric of space itself. That period, known as cosmic inflation, concluded and gave rise to the hot Big Bang, But it did not create an arbitrarily hot, dense state, nor did it produce a singularity. What transpired prior to inflation, or whether inflation was eternal to the past, remains an unresolved question. However, one thing is certain: the Big Bang is not the commencement of the universe. But if the Big Bang wasn't the start, what was it? What transpired before the Big Bang? The short response is that we don't know. The longer response is that it could have been many things, each mind-bending in its own fashion. It is conceivable that before the Big Bang, the universe was an infinite expanse of ultra-hot, dense material persisting in a steady state until, for some reason, the Big Bang occurred. This extraordinarily dense universe may have been governed by quantum mechanics, the physics of the extremely small scale. The Big Bang then would have signified the moment when classical physics took over as the primary driver of the universe's evolution. For Stephen Hawking, this moment was all that mattered. Before the Big Bang, he stated, "Events are unmeasurable and therefore undefined." Hawking referred to this as the no-boundary proposal, in which time and space are finite but lack any boundaries or starting or ending points, similar to how the planet Earth is finite yet has no edge. Alternatively, there may have been something prior to the Big Bang that deserves attention. A bold idea proposed by Professor Brian Cox suggests that there was a period before the Big Bang, a time when the universe was non-existent. He explored this in his documentary series Universe, claiming that before the initiation of the Big Bang, there was no matter at all. Only space-time and a vast ocean of energy existed, almost tranquil but gently undulating. This realm, as he depicted, should be envisioned as an immense sea of energy filling the emptiness. It would have lacked any structures, and the energy in that space would have caused it to expand violently, a phenomenon known in astrophysics as inflation. Inverting the biblical creation story, Brian Cox elaborated on the scientific narrative of creation. The crux of the narrative involves an unimaginably fierce expansion referred to as inflation. He stated, at the outset, there was a sea of energy that propelled a rapid expansion of space, termed inflation. There were ripples in this ocean. As inflation ceased, the energy ocean transformed into matter through the Big Bang, imprinting the ripple pattern into our universe as areas of slightly varying density in the hydrogen and helium gas that formed shortly after the Big Bang. The denser gas regions collapsed to create the first stars and galaxies, and 9 billion years later, a new star emerged in the Milky Way, the Sun. This star was accompanied by 8 planets, including Earth, and nearly 13.8 billion years after it all began, we appeared, blinking into the light. Notably, Brian Cox is not the sole individual to put forth such a theory regarding the universe's origin. Remarkable research in theoretical physics has unveiled a potential insight into the very early universe, indicating it might be merely the latest iteration of a cycle of bangs that has been happening for, well, at least once and possibly indefinitely. According to the research, the physics needed to understand the early universe, a wonderfully complex combination of general relativity and high-energy particle physics, can only take us so far before collapsing as we attempt to delve deeper into the universe's formative moments. The mathematics becomes increasingly difficult to resolve until it simply fails. The main indicator that we have unexplored territory is the presence of a singularity, or a point of infinite density, at the beginning of the Big Bang. Taken literally, this implies that at one moment, the universe was compressed into an infinitely small, infinitely dense point. This is clearly absurd, and what it truly signifies is that we need new physics to tackle this issue. Our current tools are inadequate to provide a solution. We require some new physics, something capable of managing gravity and the other forces combined at ultra-high energies, and that is precisely what string theory claims to be. If a physical model capable of handling gravity and the other forces at ultra-high energies exists, then string theory asserts it can clarify the universe's earliest moment. One of the foundational concepts of string theory is the erotic universe, derived from the Greek term for conflation or fire. In this scenario, what we recognize as the Big Bang was ignited by something else occurring beforehand. The Big Bang was not a true beginning but rather a part of a more extensive process. Expanding upon the erotic concept has led to a theory, once again inspired by string theory, called cyclic cosmology. Technically, the idea of a universe that continually repeats itself is thousands of years old and predates modern physics, but string theory provided the concept with a solid mathematical foundation. The cyclic universe unfolds as one might imagine, continuously oscillating between big bangs and big crunches, potentially for eternity in the past and future. As intriguing as this may sound, early versions of the cyclic model struggled to align with observations, which is a significant issue when striving to conduct science rather than merely spinning tales around a campfire. The main challenge was reconciling with our observations of the cosmic microwave background, the residual light from when the universe was merely 380,000 years old. While we cannot directly observe beyond that light barrier, if you begin to theoretically adjust the physics of the early cosmos, you influence that afterglow light pattern. Thus, it appeared that a cyclic universe was an appealing but incorrect concept. However, the erotic flame has been kept alive over the years, and recently, numerous physicists have examined the complexities in the mathematics and discovered some previously overlooked possibilities. These scientists investigate the theory of the Big Bounce, proposing that the universe is expanding and contracting, oscillating back and forth in a grand timeline. Some bouncers believe this occurred just once, while others think cyclical bouncing is what constitutes our universe. And while the Big Bounce still requires substantial leaps that necessitate generous scientific speculation, proponents argue it's far less than with a Big Bang model. They contend that the Big Bang, as described, relies on a concept called inflation. The domain of cosmology, especially regarding the rapid expansion following the Big Bang, encompasses some grand and imaginative ideas. Critics of inflation theory assert that it is excessively tidy and possibly contrived. Nevertheless, inflation implies an infinite number of universes, with our observable universe being one isolated bubble among many. This challenges the idea of a singular beginning and raises questions about what might exist beyond our own bubble. Conversely, advocates of the Big Bounce theory propose a cyclical universe, potentially offering a more comprehensive explanation without necessitating a multiverse. This theory posits that before the Big Bang, another universe existed, with entropy increasing towards the past, suggesting that time could flow in the opposite direction relative to our universe. This anti-universe concept could explain dark matter as a type of elusive particle known as a neutrino, unique to its own universe. Furthermore, extending the CPT symmetry to encompass the entirety of the universe suggests the existence of a mirror image cosmos, where every aspect of our universe alters parity, and time is reversed. This twin universe, operating under the same fundamental symmetries, could account for phenomena such as dark matter and the universe's expansion without requiring inflationary intervals. These ideas challenge traditional views of cosmology and indicate that there remains much to explore and understand about the nature of our universe. The concept of a CPT mirror universe suggests that it exists beyond our Big Bang, potentially preceding the start of our observable cosmos. Researchers propose several observable implications. Neutrinos should exhibit Majorana behavior, indicating they are their own antiparticles. One type of neutrino should be massless, a notable testable claim in this model. Inflation never occurred, as the universe naturally filled with particles. The absence of primordial gravitational waves, if corroborated by experiments, could lend support to this model. Understanding the origin of the universe stretches the limits of our comprehension. We cannot determine the initial state of the universe with certainty, which hinders us from achieving a complete theory of everything. Scientific advancement has revealed a detailed cosmic narrative, but gaps remain, such as the nature of dark matter and dark energy. The quest for the first cause remains unresolved, invoking humility in the face of the unknown. Scientific exploration, unlike supernatural explanations, relies on evidence and data rather than belief.